Well, hello, everyone. We're back here with our worksheet for chapter 28, which, as I speak, we haven't covered yet in class, but we will, and is going to be a part of the material on exam number 2, which is coming up in slightly over a week, again, as I speak. So, just a reminder, the questions that are on this worksheet are ones of a certain format that I have used on past exams. I do not guarantee that all the questions on your exam will be of exactly this format. Other question formats are possible, but understanding the material should enable you to do questions of any format. Now, we're not going to spend a great deal of time on chapter 28, which is actually why I have some other types of material on this worksheet. But there are a couple things that I'm going to expect you to get out of chapter 28. And one of the main ones that we're certainly going to get to is being able to draw the structure of a small polynucleotide. That, I think, is going to put you in the best stead for taking biochemistry later on, which most of you, I believe, will be doing. So I've already copied here into ChemDraw the structures of all the 5 nucleotide bases plus the structure of ribose. And I know I'm going to say this in class. It's made clear in the class notes. You will not have to memorize these structures for our exam. You might have to memorize them if you go on to biochem. But if you need the structures of the 5 nucleotide bases, I will give them to you on exam 2. So here's something I've asked on an exam before, and these questions all have multiple correct answers. But if you were to look for a purine that could be found in DNA, first of all, you need to know which are the purines and which are the pyrimidines. And the way I always remember is that purine is a shorter word than pyrimidine, but it's backwards in terms of the heterocycles. The larger heterocycles go with the shorter word. So the purines are adenine and guanine, and pyrimidine, which is a larger word, goes with the smaller heterocycles. So the pyrimidines are the smaller heterocycles, cytosine, thymine, and uracil. And one thing I always bring up in class, and I know I will when we cover this, is that thymine is found only in DNA and uracil is found only in RNA. So that's all we really need to know in order to answer these questions. So an example of a purine that will be found in DNA is either of these. Both purines are found in both DNA and RNA. So A or G is an acceptable answer to that. But again, notice the directions. You will not put A or G on the exam. You will put A or you will put G. Otherwise, you will not get credit. I'm just stressing that there are multiple correct answers for this. And the same thing for a purine that can be found in RNA. Both adenine and guanine are found in both DNA and RNA. And then as for a pyrimidine that can be found in DNA, again, remember cytosine is found in both DNA and RNA. Thymine is found only in DNA and uracil is found only in RNA. So for this one, I will accept C and I will also accept T. Both of those are found in DNA. And then in RNA, we will find either cytosine or uracil. And so either one of those, just put only one as the answer, but either one of those will receive full credit. And then here's a question about drawing a dinucleotide. It says, and I've even given hints on where to start here. It says to draw a TG dinucleotide with monophosphate groups on both the 3' and the 5' end. All of this we will have defined in class. The way I like to draw these structures, you certainly don't have to do it my way, but the way I like to draw the structures is to draw the 2 sugar portions, the 2 ribose portions first. So we'll take ribose over here. This is the structure of ribose. And remember that, let's see, let's put some 1 prime, 2 prime, and so forth. Prime, 5 prime. So remember, the 1 prime carbon is what we will learn in chapter 19 is called the hemiacetal carbon. Hemiacetal being a carbon with OR and OH directly attached. And then it goes around like this, 2 prime, 3 prime. And you've probably heard some of these in your biology classes. You've probably heard of the 3 prime and 5 prime carbons. Same nomenclature used here. And why are we putting primes on it? And this is something I plan to say in class. The reason that we put primes on the numbers is because we also use numbers for the atoms in the heterocycles, in the nucleotide bases. And so those numbers do not have primes. For example, if I recall correctly, it's not something I'm going to stress. If I recall correctly, the nitrogen that we use in adenine and guanine in order to make the N-O-acetal, which we're going to do shortly, in order to form these nucleotides, I believe that nitrogen is atom number 9. And those rules were decided 150 years ago, probably, in obscure journals called Beilstein that are in German. So we've got our first ribose. One thing we're also going to say is we always form a monophosphate ester between the 3 prime carbon of the first sugar and the 5 prime carbon of the next sugar. So we need to know what the structure of a monophosphate ester looks like. So we want to put lone pairs on that oxygen because it is a minus charge. And so now what we will do is bring in a second ribose molecule, since we're drawing a dinucleotide. Going to try to line that up in the right place. That's pretty close. And we'll connect the phosphorus to the oxygen. That's not working for some reason. Let's try it this way. No, still no good. Let's try this. Still working on it. So I want to connect that oxygen to this phosphorus. This is sort of like doing active homework. There we go. Finally, we're good. And we still have the CH2 in between. So it says CH2OH, CH2OH, we've got the same thing. Good, so there's a monophosphate ester. And now we can go ahead and attach the nucleotide bases. We need a thymine and then a guanine. And so we'll put them in place of these two OHs on the two 1' carbons. First a thymine. We'll attach that nitrogen at the bottom of the heterocycle to the carbon. There we go. And then we'll do the same thing with a guanine. There we go. So there's our dinucleotide. Next thing we need to consider, not that we necessarily have to go in this order, but the question says to draw a TG dinucleotide. The question also does not say whether to draw a DNA type nucleotide or an RNA type nucleotide. That's because there's enough information to tell us what we should do. We're drawing a dinucleotide that involves thymine. And as we said, thymine is only found in DNA, not in RNA. So recall that in a DNA type nucleotide, the D stands for deoxy, which means that at the 2' carbons, these OHs are replaced with hydrogens. If this had been an RNA type nucleotide, we would leave those 2' OHs there. But since it's DNA type, we will replace those OHs with hydrogens. And again, since we're using thymine, that's enough information to tell us that we're drawing a DNA type dinucleotide. If there's not enough information based on the nucleotide bases used, then it would say in the problem whether to draw a DNA type or RNA type nucleotide. But basically, if thymine's involved, then it's going to be a DNA type nucleotide and will turn those OHs into H's. If uracil is involved, then it's an RNA type nucleotide and we leave those OHs on the 2' carbons alone. So we're almost done. Now all we need to do is with monophosphate groups on both the 3' and the 5' end. So we will simply change these. Boy, that's going to continue to give me trouble. I would have expected it to recognize that CH2OH group. Of course, if you're just doing this with pen and paper, you don't have to worry about ChemDraw's weird rules. Now I know we're going to be good. So we'll change the OH into O-phosphate on the 5' carbon and also on the 3' carbon of the second nucleotide. So be sure that you know the structures of monophosphate, diphosphate, and triphosphate. Those are all fair game. And I'll just put OH groups on here for now, but since we're at pH 7, these oxygens are going to be deprotonated. And just for clarity, since those atoms have a non-zero formal charge, we'll include the lone pairs. And there we go. That's going to be our dinucleotide. And I think that's going to be good background for those of you going on to biochem, because this kind of thing is exactly not what they're going to explain in your biochem class. But the structure of a simple dinucleotide like this is something that we can understand at our level of organic chemistry. And so that's why this is one of the few things I stress out of chapter 28. You're not going to be responsible for writing essays on DNA translation or transcription or any of those other things. I'm probably not even using the right words. We'll save that for your biochem class, those of you that go on to that. But I think having a structural understanding of what's going on at the level of nucleosides and nucleotides is going to be very helpful to those of you that go on to biochemistry. Good. So that's really it for the chapter 28, the official chapter 28 material. I'm also getting in on this worksheet some practice in answering questions like this. These are questions that I have often in past years asked questions of this format on exams, and I noticed that students really struggled with it. And so I'm hoping to spend some time in class actually going over how to answer questions like this. I think this type of question should be answerable by a student in their second semester of organic chemistry. And so they're fair game for any future exam, including exam number 2. And so, for example, the question says to draw an aldehyde with exactly 6 carbons. That's something that I think you ought to be able to do. So it requires, first of all, knowing what an aldehyde is. If you don't know your functional groups, you're not going to be able to answer questions like this. So an aldehyde is a carbonyl-containing functional group in which the group attached to the carbonyl carbon is a hydrogen. So all you need to do is draw a 6-carbon compound, like it says in the directions, that includes that functional group. And so honestly, what most people will draw is the straight chain 6-carbon aldehyde. 1, 2, 3, 4, 5, 6. That's going to be the most common answer by far. And it's correct. It would be acceptable. But it's not the only correct answer. You can put branches in the ring. 1, 2, 3, 4, 5, 6. But 1, 2, 3, 4, 5, 6. That would be a perfectly acceptable answer. It is no less safe in terms of getting the points. It is absolutely acceptable. You could even go so far as to draw a 5-membered ring with an aldehyde group. It's an aldehyde with exactly 6 carbons. Absolutely acceptable. And yes, of course, you'll notice I didn't put a letter C over there. That's optional. You can put it there or not. If you use line angle drawings, then of course you don't even have to show the hydrogen. That's also a perfectly acceptable way of drawing the structure. If you put a letter C at that point intersection, though, then I think you need to show the hydrogen. But if you don't, if you use line angle drawings, that's perfectly acceptable. How would that look in our other structure? Like that. And if you chose to draw the straight chain one, 1, 2, 3, 4, 5, 6, another correct way of drawing that structure. So any isomer of this would be fine. This would be fine. If you wanted to get creative and draw something with a 4 or 3-membered ring, also fine. You can't draw a 6-membered cyclic aldehyde, though. Once you close that 6th member in the ring, you can't add an aldehyde group. There's no way to do it. So anything like that would be acceptable. Next one, a secondary amine with exactly 4 carbons. So first you need to know what a secondary amine is. And a secondary amine is defined as a nitrogen with 1 hydrogen and 2 alkyl groups. So there is a generic secondary amine, a nitrogen with 1 hydrogen and 2 alkyl groups. And it needs to have exactly 4 carbons. And there's tons of ways to do it. Probably the simplest one would be something like diethylamine. That would be a secondary amine with exactly 4 carbons. Or you could just have a methyl group on the carbon and have an isopropyl group or a propyl group. I'm sorry, a methyl group on the nitrogen. And then have either an ethyl group or an isopropyl group, also on the nitrogen. Both of those are secondary amines with exactly 4 carbons. The term secondary amine refers to the nitrogen, not to the carbon groups that are attached. So secondary amine, remember, looks like this. It's a nitrogen with 1 hydrogen and 2 alkyl groups. If there's 2 hydrogens in 1 alkyl group, it's a primary amine. If there's 3 alkyl groups, it's a tertiary amine. So I expect you to know these definitions. And that's not all. Another secondary amine with exactly 4 carbons is pyrrolidine. You can close the ring on the nitrogen. That's another one, perfectly acceptable. So any answers like that would have been acceptable, as long as it fit the definition of secondary amine and had exactly 4 carbons. Next one asks for an ester with exactly 5 carbons, so you need to know what an ester group is. And an ester is defined as the condensation product of a carboxylic acid with an alcohol. And we'll learn how to make them in chapter 21. So it's a carbonyl with an alkyl group on one side and an alkoxy group on the other. That's an ester. Again, you need to know your functional groups. By the way, since I know someone will ask, what if you forgot to put the lone pair on the nitrogen in the amine example? It's fine. The atom has a 0 formal charge, so putting the lone pair is optional. You will not lose points for not putting that lone pair in that question. The way you know you really need lone pairs is, first of all, if it's an atom with a non-zero formal charge, then it's really good to put the lone pairs. And the place you really need the lone pairs is in mechanisms, in order to be clear where the electrons are coming from when you draw curved arrows. So this is an ester, and we need an ester with exactly 5 carbons. Well, probably one of the most straightforward ways to do it would be something like this. 1, 2, 3, 4, 5. That has 5 carbons. And I don't remember the statistics for this question when I asked it in an exam a few years ago, but if I had to guess, I would bet most people put that. But there's many isomers. You could also have, if you want to make the chain branched, that would be perfectly fine. If you wanted to make a formate ester, and move that carbon over here, also fine. 1, 2, 3, 4, 5. It still has 5 carbons. So any isomer of that would also have been fine. I don't want you to think of this type of answer as any less safe for point getting than the straight chain one. It's no less safe. It's equally correct, equally acceptable. They're all esters with exactly 5 carbons. And it's worthwhile to bear in mind that there's always possible isomers that you can get by, I shouldn't say always, any sufficiently large molecule will have isomers possible. Good, and so then it asks for a nitrile with exactly 5 carbons. So you need to know what a nitrile is. A nitrile is a triple bond containing functional group. Nitriles are essentially organic derivatives of hydrogen cyanide. So a nitrile is a molecule of this type. And so to make a nitrile with exactly 5 carbons, again, I would bet you anything, nearly all of the students just added a straight 4-carbon chain to this and called it a day. And that is perfectly fine. So that's a nitrile with exactly 5 carbons. But again, isomers would have been completely fine also. So if you wanted to do something like that, That should have exactly 5 carbons also. 1, 2, 3, 4, 5. Yup, perfectly acceptable. I guess if you really wanted to go crazy and draw a 4-membered ring and add a nitrile group, you could. I don't want you guys to be scared of things like this. I don't want you to be scared to be creative. As long as you stay within the bounds of the rules, there's no reason not to put something like that. That is a nitrile with exactly 5 carbons. Absolutely acceptable. If you want to put the lone pair on nitrogen, feel free. But I would say that's optional since all we're doing is just drawing structures. Good, so I think that takes care of the worksheet for chapter 28. We'll get this up on YouTube shortly, and then we'll have everything we need for exam 2, and we'll be ready to start on chapter 19. So have a great day. I will see you all the next time.